which were silicon germanium thermocouples or thermoelectrics. And so they are connected on one side to the hot junction, on the other side to these aluminum fins that radiate the heat out to space. And then if you blow each one of those red blocks up, that's what it looks like. There are two of these hot plutonium oxide pellets that are put into graphite insulation and so on. I won't go into the details, but it's a complex geometry. And then if you zoom in to one of those heat sources, this is what it looks like. So that red pellet in the middle, the pink one, is the plutonium oxide fuel pellet that's sitting there red hot. And it's protected by metal covers, right? And these metal covers are there to protect in case there's an accident. You know, during launch, if there's an accident, you know, you don't want the plutonium to be spread all over, certain places at least. And there's a weld shield because you have to weld it shut and so on. It generates helium. One of the decay products is helium, so you have to have a way to let the helium escape. So there's a frit vent there. So it's a very complex design. It looks very simple, but it's a complex design. Because if you don't let the helium vent, this thing will explode after some time with the gas pressure on the inside. So just to give you an idea of the extremes involved, it has to survive years at 1300 or 1350 C, because that's the steady state operating temperature of this material. And as I showed you, the Cassini spacecraft took 7 years to get to Saturn and then another 20 years for the experiments. And it's got to withstand a couple of minutes, 2 or 3 minutes at 2000 C. That's in case there's a failure during launch. So it'll go up and then it'll come back down. And while it's coming down through the Earth's atmosphere, as you know, with the it'll burn up during re-entry and it'll get really hot. And simulations show that the temperatures will reach around 2000. It's got to be compatible with carbon and oxygen. In the previous slide, I showed you the blow up of what this looks like. So it's inserted into graphite insulation. And on the inside, since it's plutonium oxide, there's always a partial pressure of oxygen on the inside. So it's got to be compatible with carbon and oxygen. And you can imagine that there are not too many materials that are compatible with both C and O. It's got to have high strength and finally impact resistance in case it hits the ground. So if you look at the periodic table, there are only 9 elements with a melting point greater than 2000 C. And most of them you can't use, right? Because if you look at the refractory metals are not oxidation resistant, so they will react with the oxygen. These other ones have HCP crystal structure, and they're brittle, right? So that leaves us with iridium. Iridium has a high melting point. It has the FCC crystal structure. It's compatible with oxygen and carbon, and it has decent strength. So you don't have a whole lot of choice. That's basically what you use. And iridium is used for a few other things, right? It's used as a crucible for melting nasty oxide melts. So a lot of fiber optics are drawn in, they're melted in the iridium crucible. That's a used crucible that has seen the end of life. It's cracked. But you can melt really nasty materials, oxide glasses, for example, in iridium, because iridium is very resistant to any sort of corrosion. Aqua regia does not touch it. Pretty much no acid, hydrofluoric acid will not touch it, and it's very resistant. It's sometimes used for high-end spark plugs, rocket thrusters, fountain pen nibs. If you want to buy a fancy fountain pen, you can buy one with iridium tip. Some people like to wear belt buckles made out of iridium. Several years ago, some of you may have heard of the Motorola had an iridium satellite project, right? Back when satellite phones were the size of bricks, and they so to have enough. So if you wanted satellites to be in high Earth orbit, you would need lots of power to transmit from your handheld phone to the satellite. So to make it power efficient, you have to have satellites in low Earth orbit. But when you have satellites in low Earth orbit, then because of the curvature of the Earth, a satellite that's over here will not be able to communicate with an object over here. So you're going to have multiple satellites, right? So they figured that you needed 77 satellites to orbit the Earth. And if you remember the last slide, the atomic number for iridium is 77. And so that's why this was called the Iridium Project. But with budget cuts and everything, they had to reduce it down to 66. But they kept the name iridium because dysprosium doesn't roll off the tongue as easily as iridium does. And also kind of reminds you of something that you might take for a stomach upset or whatever. So it's an iridium satellite phone. Another sort of interesting fact with iridium is that I like to say it killed off all the dinosaurs. You know, the leading theory of what killed off all the dinosaurs is this meteor that hit the Earth around 66 million years ago. And if you plot the iridium concentration in the Earth's crust, that's on the top right there, that yellow curve shows a dramatic peak in the iridium concentration over a very narrow age. So something happened, because normally these heavy elements end up in the Earth's crust as a result of impacts or things coming in from outer space, right? Because all the heavy elements that were on Earth in the initial stages have ended up in the core that is molten, because that's where it dissolves. So anything in the Earth's crust comes in from space, but if it comes in over time, you would expect a steady, either a steady increase or a roughly constant concentration as a function of time. But right around 66 million years ago, there's a sudden peak in the iridium. So, and this has been now shown in multiple locations. And the famous meteorite that I think was responsible for the catastrophe was the one that hit in the Gulf of Mexico there. Anyway, okay, so iridium is an interesting material because even though it's face-centered cubic, it behaves like a body-centered cubic material. It shows a ductile transition. It is strain rate sensitive. So on the left-hand side are different heats of iridium, different heats of iridium at slow strain rates, 10 to the minus 3 per second. If you go to high strain rate, so 6 orders of magnitude faster, so we have a gas gun that fires a bullet, and we can do. Oh, thank you very much. Thank you.
Thank you. Now I would like to call Professor Nene to present.